required.
Okay, so is there anybody, really my question, is there anybody in here besides you that's singing the Messiah this weekend? That's really my only question.
Not that I'm aware of.
Oh, okay, well, good luck this weekend.
How are you? Did you find something covered?
Yeah. I haven't looked at it in a year, but
Luckily, they didn't change that. Although I know they changed the certain.
you're good.
Yeah, I hope you're not seeing.
It's so bad, so
The word is the lamb.
Yeah.
Yep, yeah.
It's the one piece I'm like, oh my god. We're not sheep, we are not lamb. Whatever it is, I'm always like, oh my god, not this one. I like all the others. Oh my god, you gotta go this weekend.
I'd like to.
What's your excuse?
Oh, no, I think I
Okay,
will.
okay, you should. Plus the Naval Academy is coming back, so there's
It's like 120.
massive amounts of people's and the voices are just. Yes.
I think we're just having an amendment.
Oh, are they? Okay.
Well,
Yeah, that's right.
Hair?
That's right, right, in there, because the Naval Academy gets to wear their.
Oh, it has to be hair.
I doubt it.
I don't know.
That's the person that came to mind.
Is that happening? Are you just required?
No, we're just doing it.
We're just doing it here, okay. Because I think they have enough people to do it on their own down there.
We don't.
What's that little baby button say?
The little baby button?
Oh, parasite.
Yeah!
Never mind.
Right, so where do you see them individually?
Paranoid
So you have meta for, kind of funny, for you English majors. This is for most of you.
It doesn't work though.
Void.
Because you can't have an eyeliner here. No, eyeliner's okay.
I really like to focus on
It's almost
parasite.
symmetrical in the frame.
Oh, usually tapping professor down. Lily, you read this, right?
It wouldn't
Yeah.
be quite as obvious.
Anybody go to seminar that didn't sign the sheet? Alright, so one thing, first of all, the University College Choir is singing the Messiah this weekend. I know many of you are probably aware of the Messiah dance afterwards, but if you have not heard the choir sing Messiah, right, I don't know if it's sold out or not, but anyway, it's a Saturday night performance and a Sunday afternoon performance, and it's one of those things that you shouldn't miss during your time at school. So anyway, you should try to get to that if you haven't ever been, even if you have been. Okay. So next thing, on Monday, I know that there is a physics exam, I know that there is a cell exam, and I know that I am in the middle of both of those classes. Okay. Unfortunately for you, the material we cover on Monday is going to be on your test the following Monday. Right, so if you're going to skip class either because your brain is already burnt out or you're studying for your next one, that's fine. Just know, though, that you have to get that material for the test, which is a week from that Monday. Right, so that, just saying that now, because who knows what you're gonna be doing on Monday to that class. Okay? And then the last thing, for those of you who could not go to the seminar yesterday, if you couldn't go to the seminar yesterday, I've posted this paper. I think I've emailed it to you, I don't know, I've tried a variety of things, but anyway, if you didn't get points for being in the seminar yesterday, you can read this paper, write type a 2-page summary for me that includes in that summary your thoughts on the article. Right? It doesn't matter if you liked it or you didn't like it, but just tell me what you thought about things that were presented. Okay? If you were not able to go to the first seminar, I know this is way back, but if you were not able to go to the first seminar, I never posted a paper for that. I now have posted a paper. It's actually 2 papers. It's this one called Sniffing Out Cancer, followed by New Prostate Cancer Agent Class of Molecules. So I posted this as extra credit number 2. So those of you who didn't go to the first seminar can still redeem those points. If you went to the seminar, you have the most points you can get. Don't read this and submit it again to try to get extra points, right? You have 3 opportunities. So far we've done 2 of them. And I might as well just tell you the third at this point. The third extra credit opportunity is going to be a food drive. And so you can contribute food to the food drive to get your 4 points of extra credit. We will do it after Thanksgiving, so any of you who are going home can clear out your parents' cupboards. But you should also know you can go to the grocery store now and get really good deals on canned vegetables and cereals and pastas, bless you, and things like that. So we're gonna do a food drive. I'm not going to say that the most points you can get is 4. I'm not going to say that you need to give me 4 canned good items, right? But really, what you want to do is find it in your heart to give to people who will not have what you have.
Where does the food go to?
I'm going to bring it to the food bank in Frederick. Also, if you want to bring items for pets, right? If you don't want to give human food, but you want to give cat food, dog food, just stick to cats and dogs, right? I don't know about rabbits, I don't know about any of those other things. Snakes. But anyway, stick to, no crickets, no things like that. I'll get confused. Does that go to humans? Does that go to right, seriously. But if you want to give cat and dog food, I will also drop that off at the animal shelter. So either one of those things. Okay, we'll do that after, so the week, you'll take your test on Monday, but that whole week you can bring in stuff. Okay? So that will be the third, because we missed a seminar, that will be your third option for extra credit. Okay? All right, let's go back to things. All right, so is this molecule aromatic or not? I would circle, oh, wow, I forgot one piece. Right, so right now, there's not even an option. Right now there's not even an option because of what? Right, because it's not conjugated and there's not a possibility of that being conjugated. So my bad, I meant to do that. Right? Oh, now it's much harder. Right? Okay, so answer these questions when you have the right thing in front of you. So that may change some of your answers.
Just a little.
Right, so what's the answer now? Yeah, it's still not aromatic. Right, so really shouldn't change any of your answers. Right? It is not aromatic even though it is now possible to be conjugated. Right? So it can be conjugated, p orbital, p orbital. You could make this sp2, that has a p orbital. You could make this sp2, you could make that sp2. So it can now be conjugated, but it's still not aromatic. Why? What's the hybridization of this nitrogen? sp2, I'm sort of answering this question. Actually, I don't want to answer this question just yet. If you were checking for aromaticity, then you have to say, okay, that's going to be sp2, and that's going to be sp2, because that's the only way you can have a completely conjugated system. I'm not saying these are the answers here, I'm just saying the analysis. If these are sp2, how many electrons do you have in the pi system, which means the electrons of the cyclic system? Right, so you have 2 here, 1 electron pair here, so 2, 4, 6, 8, 0, right? So you would have 8 in that system, and is 8 a Huckel number? No, so 8's not a Huckel number, so this isn't aromatic. So then the answer to this question is, what's the hybridization here? It's sp2. What's the hybridization here?
sp3.
It's sp3. What's the hybridization here?
sp3.
It's sp3. Right, and what's the hybridization here? Right, that was not involved in any aromaticity, that's just... If I wanted 6 pi electrons, and I went 2, 4, and I wanted to make this sp2, then I would only have 6 pi electrons. Why can't I do that? Because then it's not conjugated. Okay, so now I'm going to change it again. Now I put a positive there. Now what are the answers to these questions? Yes, now it is aromatic because I have 2, 4, 6, 0, and 0. And now what's the hybridization of this nitrogen? sp2, sp2, sp2. Good. All right, so now we are ready to move on to chapter 16. Remember that your supplementals from the iodo-vanillin reaction are due on Monday? Everybody's? I do have a folder in case you want to give it to me now.
Okay, I probably will,
Okay.
because I might lose it.
Okay, so let's look at some reactions of aromatic rings. You have done one in lab already, right? You either did a bromination or a nitration. But the type of reaction mechanism that you did is called an electrophilic aromatic substitution. Right, so the electrophilic aromatic substitution is a type of mechanism. It is the most common mechanism that aromatic compounds undergo. It's not the most common mechanism anywhere, but just for aromatic compounds. We call, instead of having to say all of this, we call these types of reactions EAS reactions, sort of one set of initials that you could actually say to anyone who has studied organic chemistry, and it really does mean the same thing. Right? EAS is an electrophilic aromatic substitution reaction. Please know that aromatic compounds, unlike alkenes, what type of mechanism besides cleavage reactions did alkenes undergo? Electrophilic addition, right? You added something to that double bond when you did HBr and Br2, hydroboration and acid catalyzed hydration and H2. Those are examples of electrophilic additions. Right? This is a substitution, which you remember from lab, you are substituting either a bromine or a nitro for a hydrogen on the ring. Right? So that's a substitution, not an addition. Aromatic compounds undergo substitution reactions. So, let's look at the first one. Luckily, EAS is one mechanism. It doesn't change, even though we can change what the electrophile is. So we can change this part all we want, but mechanistically it's the same thing over and over and over again. So you really just have, even though there's a variety of reagents we're going to use, you have one new mechanism to learn. So, let's look at halogenation of the aromatic ring. Right? This is the precursor to the reaction you did in lab. Right here, we're simply making bromobenzene. That's right.
Why do you have to do it in any other?
Because I didn't balance it. Right? Because remember, organic chemists only care about the organic piece. They care about the rest of it. But we will balance it in a minute. All right. So this reaction is not complete. Right, and the reason it's not complete is because remember you're doing a substitution reaction, and remember you're working with an aromatic ring. What is the stability of an aromatic ring versus the stability of an alkene? Right, so I should say that in A. Which one of those has greater stability? The ring, right? And if the ring has greater stability, which one of those two is going to be less reactive? The ring. Right? So you've seen an alkene react with bromine and go on. Now you're asking something that's not really as reactive to do the same reaction. And you know in lab that this wouldn't work. What did you add in lab? Right, what catalyst in particular did you add? Iron, right? You added a tack in there. You added iron metal in there. So this reaction requires a catalyst. Right? You need to have a catalyst to make this reaction go. In lab you used iron. In the book we use iron tribromide as the catalyst. Right, so if you use iron tribromide and this Br2 and this aromatic ring, and notice this is an unsubstituted aromatic ring, right, you get bromobenzene. What is the other part that you get to help us balance this reaction?
HBr.
You get HBr. So remember the reason in lab that you hooked up that hose over the beaker of water is so that you could catch the HBr as the byproduct. Again, when I ask you to draw the product, I'm asking you to draw the organic products. So rarely will I bother to balance this, but this is just simply the other piece of this. Okay. So, requires a catalyst. That's the FeBr3. What is the, I have to be careful how I say this. In particular, what is this catalyst doing? And there's a specific answer I want. What I don't want you to say is, what any catalyst does, right? What does a general catalyst do?
Reaction go.
Makes the reaction go fast, speeds the reaction without being consumed itself, right? Right? You memorize that in grade or something. So yes, that is true. But in this case, right, what this catalyst is actually doing, and again, we'll think about these things in terms of nucleophiles and electrophiles. Is this a nucleophile or an electrophile? Does it have electron density? Yes, so is it a nucleophile or electrophile? It's a nucleophile. Not a very good one, but it's still a nucleophile. Is this a nucleophile or an electrophile? Electrophile, right? It was electrophile the last time, it's electrophile again today. What the catalyst is doing in this case is somehow either it's making this a better nucleophile, or it's making this a better electrophile. Right? Because right now they're not going to react with each other. So you have to somehow influence them to make them want to react. So you're either trying to make this a better nucleophile or you're trying to make this a better electrophile. Right? A mediocre nucleophile will react with a really hot electrophile. You know that. You know that, right? Can you all look around? So, what this catalyst is doing in this case is it's actually making this a better nucleophile, a better electrophile. Let me be clear, okay? Because remember, Br, right? That's a pretty non-polar species. You can induce, by bringing a nucleophile towards it, you can induce some polarity in this bond, which makes this positive and this negative. But if you could really make this, instead of being a neutral molecule, if you could really make this Br+, right? Br+ is a better electrophile than Br2, correct? Right? So what this is really doing as part of the mechanism, you don't have to write this, but what this is really doing is it's reacting with the Br2. It basically pulls off Br- and it leaves you with Br+. Right? So really leaves you with a better electrophile. That's what its purpose is. So when you look at the mechanism, I just sort of wrote it like this so that you see the FeBr3 is really interacting with that bromine molecule. If this is the nucleophile, then these electrons attack the bromine, these electrons go down. Just like you had before. So it's as if, remember, this isn't a double bond, but if these pairs of electrons come and attack that bromine, what's left here? Right? Remember, we took these electrons. If this were this, right, we'd go and attack Br. Right? You get that carbocation. So these electrons come and attack a bromine, give you that carbocation. Is this a stable carbocation?
Yes.
Yes.
Right? Why is it a stable carbocation? Well, it is secondary, but what? Even better than secondary. What does it have? Oh, how quickly we forget chapter 2. Resonance.
Oh, yeah.
Oh, yeah. So you have generated, I mean, this is really stable, right, because it's an aromatic ring, but we're now going through and doing a reaction. This is a pretty stable carbocation because it's resonance stabilized. And if it's resonance stabilized, not here, but as a side project right now, draw me the resonance forms. Because FYI, everybody yesterday did a really nice job on your resonance forms. Today I just don't know because I haven't gotten that far in the quizzes. So it's not that today's people didn't, it's just that I was quite 7 or something like that. Right? I mean, really good. I mean, I love it. Seriously, you don't know what I've seen in the class.
Did you say there were 7 resonance forms on the quiz?
No. Question 7.
Okay.
There were 3 resonance forms.
Oh, okay.
No, woo-hoo. Let's just got a little mutter. Oh my God, what a freak you are. So, to get here, I simply took this bond and went there, put there, charge here. Now I've gotten this one, and I got it to here. Right? So you have a resonance-stabilized carbocation, so that's good. So, what is the next step of your reaction? Right? So the next step, and again, when I ask you to draw out this mechanism, I do not need you to draw these resonance forms unless I say draw all resonance stabilized carbocations, right? But if I'm just asking you for the mechanism, you can just write this, okay? So, here we are. What happens next? Right, so remember, you have Br minus in here. You have 2 options, right? The Br minus could simply come and attack here. If that happens, your product would look like that, correct? Is that what your product looks like?
No.
No, so that's one option, but there's a better option. Instead of attacking here, let's make sure we draw our hydrogens in. So there's a hydrogen here and a hydrogen here, right? Those hydrogens are still there. Instead of this bromine coming and attacking here, which it can do, what it really does, or what its other option is to come over here and attack this hydrogen. And if it pulls that hydrogen off, right, if it pulls this hydrogen off, what happens to these electrons right here? They fold back in and give you that. So these electrons fold back in and you re-aromatize the ring. And get HBr as your byproduct. Okay. So, the question is, the last time when I asked you, when we were trying to figure out where does the bromine go, you looked at the stability of the intermediates and said, where's that bromine going to go? That bromine is going to go where I formed my more stable intermediate. In this case, though, the same intermediate leads to the two possible products. So the stability of the intermediate is not on the table any longer because it's the same intermediate no matter which way I go. So now what drives this reaction? Why do I get this versus this? It's not the stability of the intermediate, but the stability of the product. Right? You re-aromatize, so this product is much more stable. This product isn't unstable, but relative to the stability that an aromatic ring provides you, this is much more stable. So you will go ahead and re-aromatize. Right? That is what happens in EAS reactions. This would be considered an addition reaction. Right? You added across the double bond in a sense. This doesn't happen. This happens. So when you write a mechanism for EAS, I want to see this, I want to see this carbocation, I want to see you re-aromatize. Please, the place where people make the biggest mistake is that instead of taking off this hydrogen, right, the hydrogen where you added the substituent, people try to take this hydrogen. Right? If you take this hydrogen, then you've left this carbon with what we would call a carbene, right? But they have no hydrogens on it, and you've left two substituents here, so it would never re-aromatize. Right? So you're taking the hydrogen in this re-aromatization. These electrons come in and reform that aromatic ring. That's the EAS mechanism. I can change this piece all I want. I can put any electrophile I want here. It just puts electrophile here. It doesn't change the mechanism. It only changes what your piece is because you've added a different piece. But mechanistically, it's exactly the same. So, here's my question. Sam. You had raised your hand. Anybody else? All right, so that's bromination, right? If you want to brominate an aromatic ring, you use Br2 and FeBr3. Sometimes we write it plus Br2. Sometimes we simply write it like this. There's no difference between it. It's just telling you all those things are in the reaction at the same time. So, if you want to chlorinate the ring, right, instead of putting bromine on, say we want to form the chlorine version. Instead of using Br2, use Cl2. Instead of using FeBr3, we only do that so as not to confuse counterions in the flask at the same time. Okay, so it's chlorine. All right, so that's reaction number 2. Same mechanism. How would it change? Cl, 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 right? Da, 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 da. Doesn't really change. How would I do this? All of these require a catalyst. We could use I2. That would be one way. And the catalyst we use in that case is not iron, but it's actually that. What is another way?
Sodium iodine.
What's the other piece we used in lab?
Sodium hydroxide.
commonly known as bleach. That was 2 experiments ago. Right, so you can either put an iodine on this way, or you can put a more environmentally friendly way to do it is to use sodium iodide and bleach. All right, so those are ways to halogenate. And then I'm going to add one in here. It's not a halogenation, so I don't know if you want to call it something else. It's usually lumped in the same category. I'll call it a jar. What if you want to do a nitration? I want to put a nitro group on there. Who did B? What did you use? Oh, that's why no one else doing B raised their hand. Nitric acid and sulfuric acid. Concentrated nitric acid and concentrated sulfuric acid actually mix together to form as the thing that goes here in this mechanism. When you mix those two together, you actually form NO2+. And then water. But that simply becomes your electrophile. And I do that. And I do that. And then this is going to be really your sulfate. 4 minus. Right? Same mechanism over and over and over again. All right, so let's do a double star. I want to be clear. Iodination, chlorination, bromination, those all go by EAS reactions. Nitration, EAS reaction. Right, same mechanism. This one, the next one we're going to do, is not an EAS, right? So it's sort of a side note, but it's nitro to amine. I put it in here because it relates to this. It doesn't really have its own category. This is not an EAS mechanism. I'm not going to ask you to know the mechanism. It's an example of a reduction mechanism. We're not going to worry about the mechanism. We are going to worry about the reaction. If you have nitrobenzene, and oftentimes you want to convert that, or maybe you don't want to convert, maybe you just want to make aniline. I want to go from an aromatic nitro group, bless you, to an aromatic amine group. What do I use? Tin and HCl. See, those, what you do in lab really does matter. Right? So, nitration, putting on the nitro group, is an example of an EAS mechanism. Once you have the nitro group on there, you're not adding to the ring any longer, so you're not doing electrophilic aromatic substitution. You're just changing one of the substituents from a nitro to an amine. This reaction only works when the nitro group is bound directly to the aromatic ring. Right, that aromatic ring activates this. So it only works here. Which means if you had this, and you wanted to do this, there's not an easy way to do that. Now, this is a pretty complicated route. Right, so this aromatic ring really provides density and such to make this reduction. Okay. Some of you may know people with thyroid issues. I'm going to go back to the iodination, right? Why is it important to be able to put an iodine on an aromatic ring? What is really the purpose of your thyroid? Yeah, it helps with metabolism, and it makes sort of really important molecules. And if you look at the structure of what it makes, it actually makes a molecule that has it's 2 rings. It's like a biphenyl. And it has 4 iodines on those rings. Right? So your what's it called? Thyroid peroxidase, look at me. Right? That enzyme is what is responsible for putting the iodine on the aromatic ring in your body. So if you need to take Synthroid or anything like that, and you want people to do, right, we can use these other non-enzymatic ways to do that. All right, so side notes. I'll rewrite this. Any questions? Let's jump to D. Before E is all right, so the next example of an EAS reaction is actually really important because what you're doing here for the first time is you're actually doing an alkylation reaction. And by an alkylation reaction, I mean that you are putting an alkyl group on something. Why is that important? Right, what you're doing is you're forming a carbon-carbon bond. It's the first time you've done that, right? Bromination, or HBr, you added an HX. Br2, you added halogens. H2, you added hydrogens. Ozonolysis, you cleaved bonds. But when you think about making things, when you think about synthesizing molecules, starting with something cheap and readily available, and making something pretty complex, you have to be able to make carbon-carbon bonds. And it's not easy. Some of you went to the seminar yesterday, right? What's really important is being able to make carbon-carbon bonds. And it's hard, especially when you start having other functional groups on your molecule. So this is the first way that you can do it. It's a really important way, but obviously it only works if you have an aromatic ring, because you're adding an alkyl group to an aromatic ring. These are the 2 guys, Friedel and Crafts, right? They discovered this. They're famous for it. So if you do a Friedel-Crafts alkylation, you need an aromatic ring, you need an alkyl halide. And we say alkyl halide, these are almost exclusively done with alkyl chlorides, but that doesn't mean that other halogens won't work. It's just that we tend to do them with chlorides. Okay? So, again, you have a not so reactive nucleophile. Does this even look like an electrophile? Right, but it's still a nucleophile reacting with an electrophile, and the key piece is the Friedel-Crafts catalyst. Right, so AlCl3 is your catalyst. Don't put FeCl3 in here, it won't work. Don't put AlCl3 in the chlorination reaction, it won't work. Right, catalysts again, if you went to yesterday's seminar, we have tons and tons of catalysts. Some of them will work in some cases, some of them won't. This one needs AlCl3. So, it's an example of an EAS reaction. What's the mechanism? Well, you have a pretty mediocre nucleophile. So what do you think this catalyst is doing to this alkyl halide? Making it a better electrophile. In fact, what it's doing is the same thing the other thing did. It's actually taking the chlorine and its electrons. So this chlorine, and this is far more complex than the little arrow I have drawn there, right? So it's not like, woohoo, let's just try this, right? But for the sake of you writing out the mechanism, it is. This aluminum salt will interact with this chlorine and actually takes that away, and it truly forms that carbocation. Takes that chlorine and the pair of electrons, and it leaves you with a carbocation on the atom where the halogen was. Now, do you have a good electrophile? You have a really good electrophile. So that mediocre nucleophile is now going to react with this really good electrophile. So now that you've generated that, these electrons are going to attack the carbocation. Form your resonance stabilized carbocation. What's going on?
You sound very excited.
We're just having a party out in the hallway. Sorry. It's just not paying attention. It's more.
So I went to the doctor. And I had
It's
this
so. This is so more important than this. I mean, look at that.
What does that mean?
I think these are. Even knows what this is. Is
It's
this
like a
a
different
stick
language.
figure? Are you playing? Are you playing Hangman? It looks like you're playing Hangman. Oh.
See you guys. Study for 3:39.
Yes, we talked. All right. Stick man. All right, so where were we? Okay, so anyway, this aromatic ring attacks the carbocation. You generate this resonance stabilized carbocation. What's the next step? The chlorine, it will simplify it again. You can write AlCl4 minus if you want, or you can simply write, right, because this becomes AlCl4 minus, if you use that, or you can simplify it to that. And the point is, it comes and takes the hydrogen, and these electrons re-aromatize, and you have very nicely formed
mean,
Because I have a minus charge here.
okay.
Because again, you can look at where aluminum is. This is why it works for aluminum. Right, aluminum's in the same category as boron. Right, boron, I mean, it likes to form 3 bonds. That's why we have BH3. That's why we have AlCl3. But still, even in AlCl3, it's still missing some electrons, right? Because it only has 6 and it really wants to be 8. So this Cl minus joins that molecule because the aluminum wants it, but of course the negative charge is still with it.
Okay.
This is a lot of really interesting inorganic chemistry for anyone who wants to take that. Organometallics.
She would be proud.
I'll tell her. I know, and you all were so dead to her. I was like, oh my god, she's crying. Okay, so anyway, this is the EAS mechanism, right? It's 2 steps. You have a carbocation attack, you have re-aromatizing. So, seems pretty easy. It is pretty easy, but unfortunately, there are some limitations to this reaction. Right, there are some times when this reaction won't work. The first limitation is that it must be an alkyl halide. I've simplified as X and sp3 carbon. So it must be an alkyl halide, which means that this halide has to be on a carbon that is sp3. So if you try to do this reaction, have an aromatic ring, you have the right catalyst, you have what looks like an alkyl halide, right? But it's not really. This reaction won't work because this halogen is on an sp2 hybridized carbon. So if I give you this as a draw the product, your only answer is no reaction, right? It's a limitation. The mechanism, the more complicated part of this mechanism, i.e. the AlCl3, won't pull off this chlorine. So if I gave you that, would this react with this? No, again, for the same reason, right? So it has to be an alkyl halide. You have to have your halogen on an sp3 carbon. All right, limitation number 2. Limitation number 2 says that it may lead to polyalkylation. And what that simply means is that sometimes when you run this reaction, instead of putting one group on the ring, you actually can put more than one group on the ring. Right? That's polyalkylation. You've alkylated the same ring more than once. Even if you try to say, but if I only add one equivalent here, how can I possibly add 2 isopropyls to this ring? Right? And the answer to that is that, remember, this is catalytic. So you're only forming this periodically. If you only form this periodically, after half of this has happened, what's in your reaction flask? this, half of this, half of this, and half of this, right? Because you've generated some of that. So this is present, this is present, this is present, and it turns out, which you'll learn the week after your test, that this is more reactive than this. And so once you've generated some of that, the chances that this will react over that. We are not going to worry about that, because we're not going to do it in the lab. On paper, just one adds, it's beautiful. Right? So on paper, we're not gonna worry about this, but I put it up there so that you can think if you were doing this in lab. All right. Remember, we need to finish. We have one more reaction. We have a Friedel-Crafts acylation reaction to do before your test.
Oh yeah, the one that we did already.
I was trying to figure out what do you do with what? I can't hear what you're reading. You're reading the packet. You're reading for fun. Yeah, you're reading about Keclier for fun. Yes.
Are we doing our paper though? If it's not like that where it is.
Oh no, you made that the clause. Okay, right? Because
When I go out there and not watch it.